some other dimension has the capability, or something from some other dimension has the capability of transporting a physical object into our realm.
Astronomers in Hawaii have just released what's being called the most structurally revealing imagery of interstellar comet 3I/Atlas. Captured by amateur observer COPA stars under the dark skies of Hanakaha, these images have provided a rare, almost unprecedented glimpse of a controversial optical phenomenon: a razor-thin anti-tail projecting toward the sun. Using stacked exposures and advanced AI refinement techniques, these images confirm the presence of a highly collimated stream of material, challenging the standard models astronomers have relied on for decades. And this isn't old data. We're talking about observations happening right now. The images, recorded with a Sea Star S50 smart telescope, take advantage of Earth's unique position relative to the comet's orbital plane, giving a view of the nucleus unlike anything seen before. Unlike the diffuse, chaotic comas typical of solar system comets, COPA star's data shows a concentrated, coherent projection, igniting fierce debate across the astrophysics community about the comet's composition and origin. The main focus? That anti-tail. Normally, it's a geometric illusion caused by heavier dust particles lagging behind the comet along its orbit, but the precision and sharpness of this feature in the Hawaii images is unlike anything ever recorded. Mainstream astronomers argue it's simply the result of Earth crossing the comet's orbital plane, giving us an edge on view of the dust sheet. But some dissenting voices, including researchers tracking 3I/Atlas via platforms like Space Tracker, say the structural integrity of this anti-tail implies density and mass far beyond what loose dust should allow. The implications are staggering. For a dust tail to appear this sharp and linear, the particles might be significantly heavier than standard cometary grains, raising speculation about heavy metals or dense rocky material in the nucleus. As of November 30, 2025, major observatories are cross-referencing these images with spectroscopic data to determine whether the dust is composed of ordinary silicates or something far more exotic. And this isn't an isolated observation. These findings align with a growing body of evidence throughout November, showing that 3I/Atlas is behaving in ways that defy simple categorization. The clarity of COPA star's imagery moves the discussion from theoretical models to direct observational analysis. The question is no longer whether the anomaly exists, but what physical mechanism could maintain such a precise structure against the chaotic forces of the solar wind. Let that sink in. Astronomers are now racing to analyze this anti-tail as 3I/Atlas approaches perihelion. Determining whether this is a natural projection effect or a genuine structural anomaly has become the defining scientific question of this observation window. With closest approach set for December 19, 2025, the opportunity to gather high-resolution data is closing fast. Observations like these from Hanakaha are critical. They could be the key to understanding the true nature of this interstellar traveler. Current reports show that the COPA star's imagery was captured by stacking multiple short exposures, a technique that eliminates atmospheric turbulence and achieves sub-arc-second resolution of the comet's inner coma. The resulting images reveal a level of contrast that clearly separates the main tail from the anomalous anti-tail. This observational method has been essential in cutting through the glare that obscured details in previous studies. Researchers are now focusing on that contrast. According to the technical breakdown from the team, the anti-tail remains visible for an extended duration, which is unusual for what would normally be a transient geometric alignment. Typically, as Earth passes through a comet's orbital plane, anti-tails appear and vanish within predictable windows. The persistence of 3I/Atlas's anti-tail in the Hawaii footage suggests something far more interesting: either a continuous ejection of material or a stable physical structure aligned with the solar vector. And this isn't speculation. The Sea Star S50 data is now being integrated into the global tracking database, with agencies like Space Tracker updating orbital parameters based on the new luminosity profiles. These observations refine estimates of the nucleus size and the density of the surrounding coma. The fact that the anti-tail appears consistently across multiple observing sessions in Hawaii provides a robust baseline for comparison with incoming space-based data. The real significance of the Hanukkah observations lies in the neck region of the comet. the point where the coma transitions into the tail. In typical comets, this region is chaotic, turbulent, and diffuse. The Calopa stars images, however, show an area of surprising order and linearity. This connects directly to the core mystery. Why does 3I/Atlas maintain such a coherent shape under intense solar radiation pressure? If this were a standard dirty snowball comet, outgassing should produce a ragged, uneven tail, but the smoothness and sharpness of the features captured in Hawaii suggest one of two possibilities. Either the nucleus is monolithic, a single solid rock or metal body, or it is outgassing with remarkable uniformity. Researchers are now running computer simulations to see if any combination of ice and dust ratios can reproduce the precise visual signature observed. So far, the results show a clear discrepancy. Standard comet models predict a broader, fan-like distribution of dust at this distance from the sun. The razor-thin antitail observed by Calopa stars deviates from these predictions in a statistically significant way. This deviation is exactly what's driving the current urgency in the scientific community to obtain follow-up spectroscopy. To appreciate the significance, let's look at how comet tails normally behave. A typical comet has two tails: an ion tail of charged gas pushed directly away from the sun by the solar wind, a dust tail which curves along the comet's orbit. The antitail is usually just an optical illusion. When Earth crosses the comet's orbital plane, the curved dust tail can appear to point toward the sun. But for it to appear as a sharp, narrow line, the dust particles must be large, heavy, and remarkably uniform. Here's the critical point. If the particles varied in size, solar radiation pressure would fan them out, blurring the line. The fact that the antitail remains razor-thin implies a highly consistent, uniform material release. This level of uniformity is extremely rare in natural comets, which usually spew out a chaotic mix of gas, fine dust, and small pebbles. And that's exactly what's fueling controversy. Some researchers, including Avi Low, and proponents of the extraterrestrial hypothesis, argue that this structural order hints at engineered stability. They suggest we may not be seeing just a dust trail, but a stable, structural component, or controlled emission, designed to maintain orientation. While this remains a minority view, the Hawaii data doesn't immediately rule it out. Standard dust models struggle to explain this degree of collimation. Mainstream astronomers, however, maintain that a natural explanation is plausible. They argue that 3I/Atlas could have formed in a stellar environment favoring dense, metal-rich grains, or that it may be a fragment of a differentiated planetary body, perhaps a metallic core exposed by a collision. This could account for the heavy particles needed to produce the sharp antitail without invoking artificial origins. This development is crucial. As of November 30, 2025, NASA and affiliated institutions are using the Calopa stars data to calibrate exposure times for the upcoming James Webb Space Telescope observations. The Hawaii imagery serves as a pathfinder, pinpointing exactly where to focus to capture the antitail's spectrum. The goal: determine the chemical signature of the particles. Silicates would point to a natural origin. Refined alloys would be a potential smoking gun for artificiality. We're watching science unfold in real time. The collaboration between amateur astronomers like Calopa stars and professional institutions is one of the defining features of this extraordinary observation. Because 3I/Atlas is an interstellar object, its trajectory and brightness are inherently unpredictable. That's why the continuous monitoring by the global network of Sea Star S50 users is so critical. Every sudden brightening, every structural change gets recorded. The Honoka Hawaii dataset is now considered the benchmark for ground-based optical imaging of this object. Let that sink in. The combination of exceptional atmospheric stability and ultra-deck skies provided a signal-to-noise ratio rarely achievable at mainland observatories. This clarity allowed advanced AI algorithms to refine the images without introducing artifacts, giving us an unprecedented look at the comet's inner structures. The razor-thin description of the antitail depends entirely on this high-fidelity data, which has already passed initial peer review in the amateur astronomy community. Right now, Space Tracker is integrating these images with orbital data to refine 3I/Atlas's trajectory. The results are fascinating and puzzling. There's a slight non-gravitational acceleration acting on the comet, a subtle push typical of outgassing. But here's the catch. The direction of this push doesn't align with the antitail orientation. If the antitail is a stream of heavy particles, it shouldn't generate any significant thrust. Yet the comet is accelerating. That implies a different mechanism at work, one that's not immediately visible in the optical spectrum. This is the core mystery driving headlines right now. Standard comet physics says the visible material leaving the nucleus, the tail, is also what provides thrust via Newton's third law. But if the tail is composed of heavy, slow-moving dust, it produces almost no push. To account for the observed acceleration, there must be a high-velocity gas jet somewhere, powerful enough to nudge the comet but invisible or obscured in the current images. A fundamental way of deeply understanding the ordinary world as a view from a comet, but invisible or obscured in the current images. Researchers are searching for this jet. The Hawaii data shows no bright, distinct jet separate from the antitail. This absence complicates things. It suggests the gas jets may be symmetric or diffuse, washed out by the glare of the nucleus, making them nearly invisible to our instruments. Because 3I/Atlas is an interstellar object, its trajectory and brightness are unpredictable. Continuous monitoring by the global network of Sea Star S50 users ensures that no sudden brightening or structural change goes unnoticed. The Honoka Hawaii dataset has now become the benchmark for ground-based imaging of this comet. The location matters. The dark skies and exceptional atmospheric stability above Honoka allowed the telescope to achieve a signal-to-noise ratio rarely possible elsewhere, enabling AI refinement of the images without introducing artifacts. The razor-thin antitail captured in these images has passed initial peer review in the amateur astronomy community and is now integrated into orbital models by Space Tracker. The data reveal a slight non-gravitational acceleration, typical of outgassing. But here's the puzzle. The direction of this push does not align with the antitail. If the tail is composed of heavy dust, it shouldn't generate thrust. Something else must be propelling the comet. A high-velocity gas jet, invisible or obscured in the current images. The Hawaii data shows no separate bright jet, suggesting the gas may be symmetric or diffuse enough to blend into the nucleus glow. Another possibility is that the antitail itself relates to the comet's rotation. If 3I/Atlas's pole points toward Earth, dust released from its equator could form a disk seen edge on a razor-thin wheel effect. Light curve analysis over the last 72 hours shows steady brightness, arguing against a chaotic tumble and supporting a stable rotation. But there's an anomaly. Small comets usually tumble. To maintain this stability, 3I/Atlas would need a large, dense nucleus acting as a flywheel. Observations suggest a sub-kilometer size, implying unusually high internal density. This aligns with the metal-rich nucleus hypothesis, where an iron-nickel core stabilizes rotation and directs dust release, like a shard of a destroyed planetary core, behaving simultaneously as a comet and a metallic body. This is unprecedented. The term interstellar is crucial. 3I/Atlas isn't from our solar system. Its composition reflects its parent star system. The sharp antitail is direct evidence of different formation conditions. The heavy dust, possibly metals or icy metal hybrids, is giving us a glimpse at snowline geology from a distant exoplanetary system, all through an amateur telescope. The controversy angle remains active. Advocates of the engineered stability hypothesis, like Avi Low, argue that the uniformity of the antitail is statistically unlikely in nature. Mainstream scientists counter that extreme particle sorting from radiation pressure could produce a razor-thin line, but acknowledge it's a rare phenomenon. The debate is driving unprecedented precision in modeling cometary physics. Additional anomalies keep piling up. The compact, bright central condensation in the Sea Star S50 images implies a small, hyperactive nucleus producing an outsized tail. Combined with the extreme linearity of the antitail, this creates a puzzle. Either we're seeing an unusually efficient natural process or a previously unobserved structural phenomenon. Magnetic confinement is also being considered. If the dust is charged and the comet has a weak magnetic field, something planetary cores generate, the tail could be self-organizing. This hypothesis could bridge natural and structural interpretations without invoking extraterrestrial engineering. The brightness and density of the antitail suggest prodigious material loss. If the nucleus is small, this rate cannot persist for long unless the material is unusually reflective or the release mechanism is highly efficient. With perihelion approaching in December 2025, this rate may accelerate. testing theories of confinement and structural stability. The next few weeks are critical. As Earth moves out of the comet's orbital plane, the anti-tail should widen and fade if it's a projection effect. If it remains razor-thin, standard explanations fail, and new physics may be needed. Spectroscopic analysis will be the key to determining composition: silicates, ice, or metal. Hybrid models, metallic pebbles embedded in ice, might resolve the paradox of high reflectivity and high mass. In real time, this event demonstrates the power of amateur-professional collaboration. We're watching science unfold, pixel by pixel, frame by frame, as models are tested, refined, and sometimes broken. Aside from cells being fragile, collaboration and its form, sometimes broken, the Yonoka images are now the reference point, the baseline for all future analysis. As of November 30th, 2025, 3I/ATLAS remains a sharp, bright line across our understanding of the cosmos. The upcoming weeks, leading to perihelion and beyond, will determine whether this interstellar visitor is simply a natural anomaly or something that reshapes our comprehension of cometary physics and planetary remnants.